right, welcome back. So it's time for us to resume our session after lunch, and the first lecturer is by Tim, and he's going to tell us talking about the sea and the breach in high energy physics.
Excellent. Yeah, thanks so much, Alexei. So thank you all for sticking around and coming to yet another day. So let me first start by asking, are there any questions that any of you would like to ask, maybe that may have come to mind from yesterday or from the discussions that we had in the evening or anything at all? Yes.
How do you incorporate the rising Smollett behavior in gluon pattern distributions?
Yeah, that's a great question. And it's good that you asked that because I don't really intend to discuss it so much today. That is an open issue. So this sort of physics at very low X with the low X resummation is something that's still sort of hotly debated. So often the FITs might implement some sort of resummation prescription, for instance, at next to leading logarithm. And you might imagine incorporating that and then refitting PDFs with those sorts of effects in place. And it's an open question how consequential that actually might be really for, phenomenology at the Large Hadron Collider. But there are sort of alternative fits that incorporate some of the additional sort of theory machinery that's relevant for that. So maybe during the discussion, that would also be, to ask me again, and that could be something that would be worth going into. Anything else in general or specific from discussions? If not, so the idea, I think today, yesterday I gave you sort of an overview and hopefully gave you some idea for how the PDF fits work in general. Gave you some sense of some of the open issues. Today, my intention at least is to tell you, using the PDFs as a kind of vehicle intellectually, give you some sense for where the electron ion collider could actually really be beneficial in this area. And in particular, with some eye toward a larger context, just beyond sort of specifically EIC physics, but a larger setting that involves maybe high energy phenomenology as a general sort of interest. So the idea there is, I might tell you some things that might be not as familiar to those of you who might come from something of a more like nuclear physics-y background. And if so, that's great. Please feel free to just interrupt me as was the case yesterday, or raise your hand or just shout out. I have quite a lot of material, and I'm not necessarily expecting that I would get through all of it, and that's quite all right too. So please feel free to just ask away anything that might come to mind. So again, yesterday I told you this idea that the PDFs really represent a general problem, right, in QCD, and a general problem of sufficient generality that I would argue it really is ideal as an instance that actually transcends kind of the barrier, if I can put it that way, between high energy physics and nuclear physics. And so I think should therefore really interest you just for that reason. What I did yesterday is I tried to give you some sense for the types of theory that go into the determination of the PDFs, how we actually extract them from high energy, or that is hadronic data. And I'll try to basically continue that story a little bit, maybe through a series of vignettes where I'll tell you about, a number of different types of calculations or open issues. And I should stress kind of as a preface that the examples that I choose are just that. They're essentially examples that reflect maybe my own personal background and, dare I say, my own biases really. So they're not at all meant to be exhaustive, but hopefully in totality give you some sense for what actually happens in this area. So I told you a little bit about just the notion of PDF extractions, as well as the fact that we really rely on QCD factorization theorems to all orders to empower the types of global analyses that we do in this area. I mentioned a little bit that we have specific practical interest in this enterprise in high energy particle physics. And the reason why that's the case, I suspect many of you, of course, appreciate. It's the fact that we're now engaged in a very grand endeavor to sort of test the standard model and try to identify signatures for beyond standard model physics. And Sally, just a little bit earlier in this morning, told us about one systematic sort of effective field theory approach to trying to do that. If I put it kind of glibly, however, we know that a very great majority of, if you'd like, the mass energy budget of the universe is not actually identified microscopically, we know that we have to somehow try to figure out what's going on by relying on the little bit that we do sort of understand. So to put it in kind of perhaps very overly simplistic terms, if you want to try to figure out what's going on in these dominant blocks of this pie graph, that is to say, try to identify dark matter, for example, you really want to somehow do the best that you absolutely can, understanding the tiny 4% sliver that is, as we would say, baryonic matter, essentially strongly interacting or strongly bound matter. There are various ways of going about this. I think many of you perhaps are already aware of this fact that there are things like direct detection experiments, for instance, where you might have some heavy nuclear target. You might just look for basically recoils in some heavily, highly shielded environment that might be the result of some sort of neutralino or other interaction. There are so-called indirect searches as well, for instance, like the alpha magnetic spectrometer that's based on the space station. The real vehicle for this talk, however, is collider-based searches, basically, where the notion is that I want to look for things that are not expected on the basis of the standard model of particle physics, on the hopes that deviations from standard model predictions could somehow signify the presence of novel interactions or novel degrees of freedom that are not present in the standard model. So that's what we really tried to do. So canonically, there are, if you'd like, two main sort of approaches to doing this. Again, it's a little bit of an oversimplification, but the idea is if you're looking for signatures of BSM physics, one approach is, if you'd like, the sort of discovery searches where you actually essentially directly excite some resonance or actually directly produce some sort of particle. That's, of course, what was done, as you all know very well, about a decade ago in actually finally producing and identifying the Higgs boson. That's one approach. That's the sort of discovery method. The predominance of searches for BSM physics, however, fall into a category that one might call sort of precision searches. And that's kind of typified by the plot on the right here, where it's saying, all right, I actually now have found the Higgs boson. I now want to really systematically test its nature by, for instance, looking at the patterns of decays, both productions and decays of the Higgs in many, many different channels, and actually calculating the theoretical predictions for each of those and searching basically for some sort of deviation. And that would be represented by a shift away from one, basically, in this plot. And you can already tell from doing, looking at a plot like this, that what I want is I want to be able to predict these things to very, very good precision at a place like the LHC. And I told you about this yesterday, of course. This is a little bit of review, that at the LHC, of course, I'm colliding one proton with another proton. And again, put very simply, my ability to actually perform a calculation to predict the outcome of such an experiment depends on how well I can calculate some sort of hard matrix element that's perturbatively calculable. And then my knowledge, essentially, of the non-perturbative information that resides in these red objects, the PDFs. And of course, in a sort of Drell-Yan-like process, I need the PDF of one colliding proton and the PDF of the other colliding proton, and I sort of convolute everything together in the end and calculate my theoretical prediction. So again, just to remind you, the name of the game is really how well do I know these PDFs, of course. Now, the challenge and why you talk to any particle physicist, inevitably they'll probably end up bringing up things like the PDFs, is because so many of the sort of standard candle channels or observables that we care so deeply about that are potentially sensitive to signatures of the beyond standard model physics are actually now at least very strongly limited by the PDFs, or maybe even primarily limited by our knowledge of the PDFs. And this just goes through very completely. And I'll give you some really just general sense for this. If you care about, for instance, the Higgs couplings that I was just telling you about a moment ago, or if you care about things in the electroweak sector, like precision determinations of sine squared theta W or the W mass, there was a recent anomalous announcement of the W mass based on older CDF data, for instance. These all are very strongly PDF dependent in general. And I take a little bit of an older example in this table to just highlight this as an example, where if you're looking at maybe like charge splittings in the W mass, for instance, this is based on an atlas extraction. You find that really the dominant uncertainty is actually just which PDFs do you use and what are the uncertainties on those densities. So as far as actually trying to achieve, percent level or a few percent level precision in general, you really have to confront this issue. So it's a primary need of high energy physics, and it's something that is relevant both for theory and experiments. Yes.
I don't understand the numbers. Does this mean that we have a 24% uncertainty in the PDF?
I believe the uncertainty in the splitting, for instance, this is, I think, just absolute in MEV. Yeah, so you get actually, like, I don't know, do the math in your head, 80–90% or something is really driven by the PDF knowledge. So if you wanted to actually find a charge splitting. So it's a big effect. Oh, one last point. You might think, I don't really have to care so much about any of this because, well, I'll just get more data, essentially, and that will take care of the problem. In fact, that's not really the case because, in fact, a lot of this ends up being systematics dominated, of course, too. So having just more statistics doesn't always help. And I might give you also some sense for why that can actually be the case, why statistics can, in some cases, actually even make the problem a little bit more challenging to sort through. Any other questions before I show you a few of these examples? Okay, so all that was kind of just a bit of a preface. Now, what I want to do is just show you, just highlight a handful of examples of where this actually really comes about. So I mentioned just a moment ago, electroweak physics and electroweak observables and the fact that they're PDF dependent, for instance. So you might want to do, as I just showed in the previous slide, producing W plus and W minus bosons and trying to measure things like charge splittings to very high precision. Well, of course, if I want to actually just predict, this is essentially just, of course, leading order, but just to give you an idea, if I want to calculate basically some rapidity dependent W minus production cross-section like this, I see that obviously there's some dependence, of course, on the down type PDFs in general in this case. So how well I can actually predict this cross-section depends on the extent to which I'm aware of the X dependence in both the down and the strange PDFs. And this is particularly relevant because there's a straightforward connection between essentially the rapidity measurements that we match in something like W boson production to the actual partonic X momentum fractions that you evaluate the PDFs at. So for instance, if I were looking at maybe a ratio of the W, I believe this would be W minus to W plus, actually, that's a typo. Oh, excuse me. This is just W minus production normalized to a reference calculation. You see that actually, if I go to sort of large rapidities in the produced W boson, there's actually a significant dependence on how exactly I treat nuclear corrections that actually influence the down type PDF, for example. And similarly, if I were to look again, maybe now at like a charge splitting sort of observable, so looking at W plus versus the W minus correlated cross sections, again, there are very sizable ellipses that are really substantially driven by our knowledge, both of the down and the strange PDF content. What I just showed on the previous slide, if you want to actually get good knowledge about the down PDF, where might you get that information? Does anybody have a suggestion? What types of observables would I want to look at if I wanted to get sort of like flavor separation or flavor dependent, access to the down PDF specifically? Those of you who might be, DIS, tritium versus helium. That might be one example. I was thinking of something even simpler, actually. Neutron. Sure. Yeah, but why can't I do that? Well, because the neutrons, they go away. Half of them go away. Yeah. So I don't have a stable neutron target, right? Of course. So if I wanted to do like, DIS sort of like fixed target experiment, as opposed to just doing a fixed target measurement on the proton, that would be dominated by the U-type PDF content. Then I could do it on a neutron if I had an actual free neutron target, but in nature I don't. So sort of the next best thing is to actually do a measurement on deuterium, of course, but then there's actually a nuclear correction in that case. So that's actually the point of the yes. This is a ridiculous question, but how come, if you get enough of them, if half of them go away after 15 minutes, you could
still do something if you did it fast. That people-
Yeah, I mean, I think if you want to have, sort of a stable experiment with a stable target, I think the best thing to do is, have an actual nuclear bound state, of course.
Protons.
Yeah. Now there is theory for actually how to do this in general, of course, but it depends, of course, on how well you actually know a theoretical model. So this is the process. I have maybe some charge lepton, it comes in, it exchanges an electroweak boson, in this case a photon, and you interact in particular with the neutron that's actually now bound inside the deuteron target. But then there's some sort of nuclear correction that influences basically the partonic structure, and especially at high X actually, and that's what's shown, for instance, in this plot. If I have knowledge of some sort of distribution or something like a spectral function that tells me how a nucleon is actually distributed inside the deuteron, then I can convolute that with nucleon level information. And the end result of doing such a prescription is that in general, if I then extract something like the d quark, or in this case, the ratio of down to up, you get this very substantial correction, particularly at very high X. It just so happens to be the region in X that's particularly relevant for sort of the large rapidity measurements in W production that I showed in the previous slide. So even though you might naively think of this as sort of like a low energy measurement, it's certainly very good fodder for the electron ion collider, and it's actually very consequential for high energy phenomenology, because actually the W production cross sections depend on how well I can actually do this. There are analogous situations where we talked about this a little bit in the discussion last night. If I want to try to unbury the strange content of the proton, it's really, really hard to get access to the flavor separation. So many FITs make recourse actually to performing DIS actually on heavy nuclear targets, where you have a similar problem. I have to understand how a nucleon is actually distributed inside a heavy nucleus like iron. And I'll go into that in just a little bit more detail in just a moment. Now, what I was just talking about was the high X PDF uncertainties. And you might naively think, based on some of the discussions that we had yesterday and in the talk yesterday, that, okay, I care about extremely high energy physics if I'm high energy physics if I'm doing the LHC, and that's immediately connected to the low X behavior of the PDS. And so who cares about high X? It's actually not quite that simple. And I showed you the answer on a couple of slides ago. Does anybody remember why should I care about high X if I'm doing some measurement at the LHC? Why would high X ever matter? Yeah, exactly. I mean, it depends. I showed you a formula actually. So you just would have to sort of invert this expression. So actually, if I'm thinking about large rapidities in general, even if I'm at root S of say 14 TeV at the LHC and I'm producing a W boson or something, that weights me toward, of course, very low X in general, but then I'm exponential in the rapidity. And if I look at very large rapidities, ultimately the pretty high X behavior still is relevant. And actually it turns out that many people search for new physics, perform analyses looking for signatures of BSM sort of in the tails of rapidity distributions. And it just so happens that, of course, how well you understand the high X PDFs and things like the high X anti-quark PDFs influences your accuracy, basically, at these large rapidities that might be BSM sensitive. Now, the errors at high X are actually rather difficult to tame. This slide is meant to give you some sense for this, for instance. So, and it depends, again, this is something we discussed yesterday, how exactly I extract the PDF uncertainties. I've told you a little bit about the fact that we have sort of Hessian formalism in one set of PDFs. We have this sort of Monte Carlo based uncertainty determination in FITs like NNPDF and others. One thing that's really challenging, however, is the fact that just actually sampling the uncertainty adequately with enough Monte Carlo replicas is actually very challenging. And if I'm talking about very high X, there are not really that many data that are actually sensitive to the high X behavior in the PDFs. So it just so happens that because of that, you're very heavily extrapolation dependent, and it depends on the underlying model quite significantly. And in general, you're not necessarily even always guaranteed unless you sample, if you take a Monte Carlo approach, very, very good. You can actually get even unphysical behaviors where the extremely high X uncertainties can lead to negative cross sections actually. And that's illustrated in this slide, for instance, for sort of TeV scale Drell-Yan production cross sections. So what's often done, we heard a little bit about this from Sally a little bit earlier in the morning. If I have a negative cross section, I know immediately that that's bad. And so that hints already that something's going wrong in principle in terms of how I'm actually sampling the uncertainty in the PDF. So again, this is something that is really worrisome. That was a little bit about electroweak physics. You have analogous problems if you're trying to think about Higgs physics. And again, we're really interested in the Higgs because it's a fundamental particle, of course, and its couplings in general to maybe CC bar or other QQ bar states or all the rest of the fundamental content in the standard model really tells me about, in principle, what might be going on beyond the standard model. So it attracts a great deal of interest. However, Higgs physics is similarly very, very PDF limited, just as I had explained earlier. Which PDFs would you guess should I care about if I'm trying to do the best that I can in terms of theory predictions for the Higgs boson? Does anybody have a guess? I think it might literally even be on the slide. The gluon. Yes, exactly. And that's because actually these types of fusion diagrams really account for something like maybe 90% of inclusive Higgs production in general. Just glue to glue goes to the Higgs. It generally proceeds usually through some heavy quark loop. Which heavy quark is the most relevant in this diagram? Top. Exactly, the top, of course. So, but in any case, how well I can predict this really depends on how well I know the parton densities of the colliding protons and the glue content in particular. And it just so happens if I ignore any sort of differential dependence on kinematics, but just look at sort of total cross sections for gluon fusion induced Higgs production at, say, next to leading order, there's actually really quite a substantial spread in terms of the theory predictions based just on which specific PDFs you choose to do the calculation. So that's bad. That's not what we want. So if you want to really improve this and sort of enhance the discovery potential at the LHC, at least as far as Higgs physics is concerned, you'd like to actually know things like the gluon PDF better. This is a little bit of a technical slide going into this in a little bit more detail. It's to say that often what I care about if I want to think about actual Higgs production cross sections, I might think, of course, about the gluon PDF, as I just said, but something like a parton, which is to say the glue to glue luminosity that I can calculate, and that's directly derived from the gluon PDF. You might wonder if I do an actual analysis where in terms of the gluon PDF, where kinematically is most relevant for the Higgs production. And actually, we can maybe go into this a little bit more detail in the discussion. I leave it to you to maybe work out this and think about it and make sure that it's correct. But in general, what's most relevant is maybe something like 0.02, x of 0.02, and maybe something comparable to the Higgs mass in terms of the scale for the gluon PDF. And we struggled really quite mightily to try to improve the PDF uncertainty in this relevant region. What this plot shows actually is basically the size of the uncertainty. So there are ratios of several PDF fits with a baseline, actually, an analysis from a few years ago, this CT14 Hera2, all of these are next to leading order. That's sort of the baseline, and shown, I believe, in sort of the like this gray band. The top, the CT18 NLO, which is shown in sort of this purplish color, is a new fit that includes a great deal of run one data from the LHC. And what you'll notice in a plot like this, especially if I keep gesturing at this sort of intermediate region in the plot that's relevant for Higgs production, is that the improvement in the band is really quite modest, despite the fact that I've added in a great deal new data. Why might that be? Does anyone have a guess? Why, what could be going on in this case? Why, I mean, if I have a whole bunch of new data, I fit them, shouldn't I just get a tighter uncertainty in general, or why wouldn't I? Does anyone want to venture a guess? Yes.
Uncertain.
Yeah, something really closely related to the systematic uncertainties, and partly yes, exactly that. Really just the fact that you might have you know, competing polls from the various data that you fit, right? They might not all perfectly align. That's just one guess, of course. You could also ask questions, maybe I need, you know, n cubed LO theory accuracy to get more out of the available data, or maybe the polls of one set of data has to do with some incompleteness in the basic theory that I just described. It could have to do with what I showed a few slides ago, where some of the data come from nuclear targets that could be better fitted with an improved nuclear model, for instance. All of these types of things are relevant. Whatever the matter, however, really what really ends up being quite important is the question of just the compatibility among all of these fitted data sets. And what's shown in this transparency is just the variation in the global chi-squared in black, and then the variation in the chi-squareds for each of the various fitted experiments. This isn't all of them. These are particularly noted experiments that vary, have larger variations in chi-squared. And what's specifically being shown is the change in chi-squared as I vary the value of the gluon PDF at that sort of Higgs point, if you will, at x of 0.02 and at q comparable to the Higgs mass. And what you find is, if I look at the total chi-squared for the entire fit, everything, of course, is, if you'd like, sort of normalized or set at the preferred value of the fit starting off. And then I just essentially tune or dial away the value of this gluon PDF and either make it larger or smaller. The total chi-squared looks really quite nicely parabolic, but the chi-squareds for each of these various fitted experiments do all kinds of crazy things, of course. And what you find is that some of the experiments, for instance, this E866 was a fixed target Drell-Yan measurement at Fermilab, protons on fixed target protons. That tends to have an improvement in chi-squared, which is to say that delta chi-squared gets less as I increase the magnitude of the gluon PDF at the Higgs point, whereas some of the other experiments, for instance, maybe something like this CCFR data, which is actually neutrino scattering data, that does just the opposite and pulls in just the opposite direction. So having these, you know, competing polls among the various fitted experiments ends up being really a challenge that we have to sort through, and it is actually an impediment to higher precision in these types of fits that we have to grapple with. And the other thing that I also wanted to highlight, again, given your interests in the electron-ion collider that I think are particularly notable, is the fact that some of these measurements that I just mentioned, okay, a few of them, you know, there's things like, okay, Atlas inclusive jet production data, something similar from CMS, of course. Oh, that's sort of unsurprising, but some of the other experiments that have really non-trivial polls on the gluon and are thereby connected to Higgs physics are things like this, like fixed target Drell-Yan cross-section that's, you know, at the level of like order 100 GeV or something, or some sort of neutrino scattering data that's even lower energy principle. So those end up being actually relevant for Higgs physics. So that's something that I would request that you sort of keep in mind going forward through this talk, that's actually the case. Now, somewhat shifting gears, are there any questions, by the way? Okay, yeah, please.
Go back to the first.
Sure.
First, I'm very confused. So why chi-square can be negative?
Yeah, thank you for that. Very good question. So what's being plotted here is the shift in chi-squared. So actually the global chi-squared, they're maybe fitted, you know, 4,000 to 5,000 total points. The global chi-squared for the full fit is comparable to the number of data points that are actually fitted. What's being shown is actually the shift in chi-squared from the best fit value. So that's why, so I mean, a negative value of delta chi-squared corresponds to an improvement in chi-squared relative to that of the best fit, basically. Yeah. Are there any other questions? Okay, great. Okay, so I've given you some sense for a couple of key observables. I mentioned W production, Higgs production, these kinds of things that LHC physicists, we all talk about, of course. The other thing that I want to just drive home is, again, the fact that, the state of the art in a global fit, as I tried to convince you yesterday, is in general at least next to leading order now. And so we have complete theory, at least in general, to next to leading order. And increasingly, actually, the next step beyond this is N3LO, of course. And with that theoretical machinery and our knowledge of the PDFs, we can calculate all manner of various cross sections, including those at 14 TeV. And so, again, just to give you an idea for the magnitude of the problem, basically, I can look at all kinds of different things. I can look at sort of Higgs production cross sections at 14 TeV against TT bar production cross sections. That's sort of in the QCD / Higgs sector. I can look in the electroweak side of things, the W versus the Z production cross sections. And again, what I want to stress is these various ellipses are really the PDF uncertainties. And there are two effects, right? Any given ellipse has obviously a finite size that's just driven by the PDF uncertainty in a given analysis. But then there are basically systematic shifts in these ellipses where the best fit value is somewhat offset. And that's particularly pronounced, at least just in this example, in the right-hand panel. If you look at a particular fit, which is the CT18 sort of default analysis that inside the CTEQ group was our last main fit, that results in one series of predictions and uncertainty for W and Z production. But I can make basically systematic choices in how I do the analysis. If, for instance, I do or do not include a particularly sensitive data set that's connected to this strange PDF, that's this 2016 7 TeV Atlas inclusive WZ data, I can actually really shift the prediction quite substantially in terms of the sort of relative size of the PDF-driven uncertainty, going from sort of the black cross to the blue bullseye at right. So again, there are these significant PDF-driven uncertainties that aren't just, the errors in a given analysis. It really comes down also to just looking at the total state of play in terms of all of the PDF fits that are available to us. And there are various methodological or other choices systematically that are made in these fits that constitute a larger uncertainty that impact these various LHC observables that we still have to actually somehow improve and get under better control. Now, continuing sort of the thread that I was just describing in the electroweak sector, you can think about other maybe weirder processes that may have not occurred to you. And I told you particularly yesterday a little bit more about the fact that we are really interested in next to leading order accuracy in terms of perturbative QCD. But you may well think to yourself as well, okay, I do quite well in terms of the perturbative QCD, but what about electroweak corrections? And at some point, it no longer makes sense to just keep kind of turning the crank as theorists and increasing the theoretical sort of accuracy only in one area of the standard model. So at some point, if you start thinking about electroweak corrections, and for example, next to leading order electroweak corrections, you begin to have non-trivial diagrams at next to leading order in the electroweak theory, for instance, that come into play for observables like coincident W plus Higgs production. And I added this plot because it came up something relevant in the discussions last night. And the incredible thing, and by the way, I mean, these are the types of observables that, again, are very much of interest if we're trying to think about, possible BSM signatures. If I look at an invariant mass distribution for a process of this type in the invariant mass of the W plus Higgs pair, and I look at large invariant masses, and again, it's sort of the tails of these types of distributions that have putative BSM sensitivity, it just so happens that if I neglect any of these next to leading order electroweak corrections, I get one series of predictions in terms of the invariant mass distribution, and I get a very substantial takeoff, especially if I look at it as a fractional effect, if I include the next to leading order correction in the electroweak sector. But once I have next to leading order corrections, then I have at my disposal now different types of diagrams that are relevant. And in particular, this one that I keep gesturing at, where there's now actually scattering of the quarks in one proton from the photon in another proton and PP scattering. And it just so happens that you therefore really have to think about now not just the quark gluon content of the proton, but actually the presence of an explicit photon PDF. And I wanted to add this because of the gist of the recitation that we had last night. We had this question, what exactly is a parton anyway? And maybe I can ask it again now that you're all a captive audience. What is a parton? Does anyone want to say?
Everything.
Basically everything that's like allowed by basic fundamental symmetries at this level. It's, you might naively think, an up quark, a down quark, the gluon, of course, and I'm done. No. So you have the photon. In principle, you could even have other standard model content as well present in the proton, where you'd have to do, again, just according to the standard technology, some sort of resummation that would lead to a non-vanishing PDF, however small. And it's particularly phenomenologically relevant, which is to say not zero, if you think about the photon PDF. And I just explained why that's the case. Yes.
Someone said something last night about them, the quarks exchanging also W bosons.
Yes, no, absolutely. So a couple of my colleagues, in fact, even put out a paper on electroweak boson PDFs. They're incredibly small. I mean, electroweak bosons includes, of course, the photon PDF that I'm going to talk about for a moment, but then, yeah, the weak bosons as well. They're very small in general. So
I should be able to know, I should beforehand that they're going to be very small. How do I know that?
Well, I mean, part of it comes from, well, various things. I mean, you know that there's a sum rule, obviously. I mean, there are more empirical arguments why you would come to that conclusion versus more theoretical arguments. And maybe, at least at the moment, I'll err on the side of saying, okay, we fit the PDS really quite well in general. You can get sort of chi-squareds that are comparable to the degrees of freedom and comparable to the number of fitted points in general without adding in all of that sort of stuff. And so you know that it works relatively well. And we also have momentum sum rules, as I was talking about in the discussion last night, that tells me that if I integrate over a first moment basically of all of the quark and gluon content, never minding any of this other sort of stuff, then I'd better recover one. And in general, all of these things work relatively quite well. That said, on more formal grounds, I know that I have some incredibly small contributions from things like the photon PDF, for instance, or some of this other stuff as well that could potentially be present too. That's especially small. The photon PDF would contribute to the momentum sum rule that I was just talking about, but at sort of like a sub% level. So it's again, the total normalization is quite small. Are there other questions or comments? Okay, so I'll just keep going. I won't really belabor this too much because it's sort of technical a little bit, but there's new formalism that emerged just a few years ago, actually, for how to actually calculate the photon PDF in a systematic way that's valid sort of to all orders, both in QCD and in the electroweak theory. And basically what it comes down to, and we can go into this in the discussion if it interests anyone, you calculate the X-weighted photon PDF and the proton at a particular regularization factorization scale, and it boils down to your knowledge of actually the F2 and the longitudinal structure functions of the proton, actually in this case integrated over a very wide reach in Q squared. And that reach in Q squared kinematically, that's relevant for this type of calculation, goes down to quite low Q squared, where the structure functions are dominated not purely by perturbative QCD type physics, but actually non-perturbative stuff as well. And what you do in this case actually influences basically the magnitude of the photon PDF that you extract. And in particular, if you were to decompose the calculation and get the photon PDF just in one particular sort of run of this type of analysis, the contributions to the total photon PDF through the structure function of the proton that I was just talking about, particularly at high X, a lot of it ends up actually coming from things like target mass corrections or higher twist effects or various other non-perturbative physics that's sort of the purview of the electron-ion collider. So that stuff ends up actually, again, even if you're talking about the weirdest possible things that if you're a nuclear physicist, you might never think about W plus Higgs production so much in your career. You might think, on the other hand, all the time about twist 4 corrections to the proton structure function. That ends up actually being really quite important and relevant in this area. And again, the EIC will actually really help unravel a lot of that type of physics. And so that's another point of contact where the EIC rests inside this larger landscape of all of this interesting stuff. So if you wanted to think about, in like some electroweak structure function, just taking a favorite example, maybe the F3W plus structure function, and want to think about its behavior at low Q squared, and low W, which equivalently is to say low Q squared and high X, correcting for the non-perturbative nature of the proton ends up resulting in a sizable fractional effect in the structure function. And that's what's shown in this plot, for instance, showing actually the target mass correction, both its theoretical prescription dependence and just its general size, basically, that as I go to very low W. And so this ends up influencing actually the photon PDF calculation that I just showed a little bit earlier. So having this type of physics under control will ultimately influence electroweak theory at the LHC as well. There are, again, just continuing this thread, many different observables that are of interest, of course, that are PDF dependent. One is the ultra high energy neutrino production, which is something that my colleagues and I looked at very recently. If you want to look at, again, something like really high energy neutrino production. This is not terrestrial neutrino physics, but instead something like cosmic ray physics or a neutrino telescope like IceCube. In general, what happens is you find that the PDF uncertainties get larger and larger as I go to these high energies. Does anyone have a guess why that would happen? What exactly is driving this? So this is basically just a plot of the uncertainty in several different calculations for this very high energy neutrino cross section. Why on earth, when I go to 10 to the 10 GeV for, IceCube or one of these very high energy measurements, ultra high energy measurements, what drives the PDF? What drives the uncertainty in this case? Yeah.
Because you only have a couple events, or
well, this is just a theory prediction. So yeah, this is purely theory. You're right though. There's very little data, of course. Well, I already kind of said in words. I mean, it's a PDF uncertainty, but where and what? Well, if you pay close attention. And the hint, of course, is as I keep extrapolating to high energies, you'll notice that these uncertainties apparently just become basically uncontrolled. Where do the PDF uncertainties become so badly small x? Yes, exactly. So this is, at some point, I have almost no knowledge of what's happening in terms of the small x behavior of the PDF. So as I keep going off the charts to arbitrarily high energies, for instance, at a neutrino telescope at ultra high energies, where you might look for signatures of, say, extra dimensional theories or something, then actually the fact that I have no idea what's going on at low X for the PDFs becomes the problem. I think I'm going to skip this, and just in the interest of time, but I was just going to say basically very quickly that was really high energy neutrino scattering. Inside the HEP community, a huge amount of the effort is now devoted basically to preparations for things like Dune and searching for signatures of CP violation, for instance, in the neutrino sector and the origin of the matter-antimatter asymmetry. All of that entails doing some sort of neutrino flavor oscillation search that's now sort of GeV scale. So not ultra high energies, but GeV scale physics. And in that case, what you're doing is you're looking at sort of coincident, detection of neutrinos, both at a near and a far detector, where the interaction is with some heavy nuclear target like argon, for example. So in that case, I have to know the GeV scale neutrino nuclear interaction, including neutrino deeply inelastic scattering that is heavily dependent on PDFs. And in that case, actually, the nuclear PDFs in particular. And what I wanted to stress here is that you can do for nuclear PDFs more or less the exact same thing as what I've spent both today and some of the time yesterday describing. I can write down some sort of flexible parameterization for the nuclear PDFs. What would be interesting about the nuclear PDF parameterization? Does anybody have a guess? I would parameterize obviously the X dependence, I would assume, much as for the proton for the LHC. What else? Yes.
Oh, there is also a bunch of different effects like cold nuclear matter stuff and things.
Yeah, that's it. Yeah, so I might want to think, I want to understand sort of nuclear matter effects and how they influence specifically maybe the partonic structure of the nucleus. And I mentioned this as motivation yesterday. How would I do that in principle? How would I go about doing that?
Modeling that?
Well, maybe I could do something that's model independent though, and I don't want to model it. I just want to measure data. I want to do a QCD fit of some sort without a model.
Smearing from Fermi motion?
Well, I mean, let me just tell you. So, I mean, the idea is, of course, I would want to do these measurements. Maybe I'd have deeply inelastic scattering, maybe neutrino-initiated deeply inelastic scattering, as I was just describing, on many different nuclear targets, right? And so what I was getting at is, in principle, you wouldn't just do this on iron or argon, but maybe carbon, maybe many different nuclei. And what this does is it introduces an additional sort of degree of freedom or dimension into the fit. So I'm no longer just fitting the X dependence as I do for the proton. I now also have a nuclear A dependence as well. And I can parameterize that freely as well. And so the idea is, you know, I have the same sort of QCD machinery in terms of factorization theorems. Maybe I have to work out some aspects that are unique to sort of the nuclear medium, but I otherwise do the same thing. What's another challenge? What would be hard about doing this in particular if I want to learn the X dependence and the A dependence and all the rest, if I were doing a nuclear PDF fit? Well, I have yet another whole dimension, obviously, that I want to fit. So I need a lot more data. So that's the challenge. And in principle, if I want to smoothly parameterize the A dependence, just as I do for the X dependence, then I would need many different nuclear targets and different nuclear species to try to perform such a fit, ideally. And so that's an additional challenge, of course, in this area. Yes.
Does that challenge preclude splitting A up into A universal? There's going to be some effects that are universal to all nuclear, like the Fermi motion, and then A, which is A dependent.
Yeah. You could always try such things. I mean, my attitude is the best thing is always to be agnostic about what exactly is happening. And I think, maybe I'll get to this at the end, but, the aspiration is really to be in this area when you actually do the analysis as model independent as possible, so that you're not saying, oh, here's this series of assumptions, let me test, let me, now do an analysis on that basis. Let me get away from that. Let me just test things that I can improve systematically, like the perturbatively calculable QCD. I can get more data, not just more data, but data and maybe that I didn't have, different new types of data. And I can maybe improve the parameterization in some way, make it more flexible and so on, but I don't make any assumptions. So you could always try to do that same sort of thing and parameterize the X and A dependence as flexibly as you can, get a fit, and then maybe in that context, you might try to match on to some universal, scaling in A or some other types of assumed effects. That's I think maybe the way to do it in general. Are there any other questions about this idea? This is, I think, wanted nuclear PDFs to make an appearance, at least in some brief form at this meeting, just because they're actually quite important, particularly since high energy physicists now care about neutrino scattering quite so much. So, okay. If not, I'll just keep on going. So I mean, ultimately you do the fit and then just exactly analogously to what I showed before, then you can look at nuclear PDFs and their uncertainties. In this case, again, for argon at a particular scale, just as I was talking about before. So in the last few minutes, what I want to do is just jump through sort of how does the EIC come in to all of this picture. I gave you, again, a very quick half-hour sketch effectively of, oh, this is a problem, this is a problem, various things that are afflicted by our ignorance, basically, of hadronic structure in high energy physics. The EIC, as you all know, is really a machine. It's a QCD machine that will sit, kinematically in a unique area of, for instance, the X and Q squared plane that will give us a very effective lever arm in principle to understand things like the scaling violations. We'll have at its disposal many precise measurements that will allow us to unfold the PDF. So somehow it will be important, that much you can say. And indeed, this is something that was, we looked at really quite extensively in the context of the EIC Yellow Report, for instance, trying to just understand how, if you do a particular global fit with a particular baseline, how those assumptions and how a particular set of EIC pseudodata might result in improvements in the PDF uncertainties. And in general, what we found is that, the EIC has really quite a substantial impact. Particularly, it actually turns out, at least in the yellow report, findings on things like the high X up and down PDFs, probes of the gluon content, just as well at low X. This stuff was all based on basically inclusive EIC measurements, where the idea is that you're just taking just totally inclusive electron proton or maybe electron deuteron mediated by either charge or neutral current interactions, and not thinking about some detailed elaborate tagging in the final state or something like that. And what you find is already at that level, just thinking about maybe in 100 inverse femtobarns of data or something like this, you get just inclusive data-driven improvements in the PDF uncertainties. You can go further than this, however. And in fact, that's another point that I really want to stress to you all as this audience for this school, is that inclusive measurements are really interesting, and they might be sort of the first order thing that would occur to you for trying to probe the PDFs, much as have been the experience at HERA. But then what's also intriguing is, having measurements that could help dissect maybe the flavor dependence, as I was describing a little bit earlier. And one thing that's helpful, for instance, in this case, might be something like a charm tagged or charm jet production, for instance, maybe mediated again by this charge current interaction, where in this case, I have an electron that comes in and exchanges a W boson. And then because of the charge nature of this elementary interaction, just again, in this leading order diagram, you resolve actually the strange content relatively well by doing this final state tagging of the charm net that's produced in the final state. This could be a challenging measurement, but the idea is you have very high luminosity and you have in principle the capabilities to get these sorts of data. And the idea is this is again just looking sort of at event level and things like this. If you consider different scenarios for how this strange PDF might behave, which is all of this crazy mess of tangled curves, you can feed these in and basically predict, again, at event level, how, for instance, the reconstructed PT of the charm jet might go basically in one scenario in which the strange PDF is actually sort of relatively small. That's shown in sort of this pink points and the associated lines, or an enhanced strange, for instance, which I showed on the previous slide. And you find that you can get really quite big jumps in terms of the events, basically in the reconstructed PT, and that effect is quite large relative to the projected sort of statistical or discriminating power in a measurement like this. So the idea is that, again, you want to have measurements like this that are more sensitive as well, that can help you with things like the flavor separation, for example. I wanted to very quickly mention as well that was sort of about the strange content. I detected from several of you this interest in somehow the charm physics as well, and this question of the non-perturbative charm. And it came up a little bit in the discussion last night, as well as I think in the talk a little bit earlier. I tried to explain to you yesterday some of the subtleties of how the purely perturbative calculation goes and how typically the default assumptions for the charm physics happen to work. And the idea, as I told you before, is that we usually assume that the charm is entirely perturbatively generated. So if I start basically with my generic sort of factorization formula for the charm and the proton, I might start at the charm production threshold, assuming that the charm PDF exactly vanishes there. And then at scales larger than that, I generate the charm purely through sort of, perturbative diagrams that I just calculate, to a desired order perturbatively. You may ask, can't I have some non-perturbative component that I would basically freely fit? Could I have basically some sort of intrinsic charm, the older language to refer to this idea? And the idea there is that I can basically calculate, maybe in the context of some model, basically a 5-quark Fock state of the proton that contains, in addition to the UUD light quark content, a CC bar pair. And typically in a standard sort of model calculation that you might do of this nature, that usually ends up producing like a large X or a valence like bump, like for the charm at high X. And the question is can I try to actually distinguish something like this in a global fit? A subtlety that I would point out is you might refer to this prescription really as actually just fitting the charm, because we don't necessarily have a firm grasp on the actual non-perturbative dynamics that would really be in play here. I can model it, but that's not quite good enough at this level. What I wanted to point out is that, at least in the context of like the CTEQ fits, we still don't have really any clear signal for significant non-perturbative charm. We have colleagues in, for instance, the NNPDF group that recently announced that they do have some evidence that they've observed. We don't see that, however, and the way we go about doing this is, again, by fitting charm, which entails actually just taking really like a range of scenarios for the Hayek's behavior of the PDF, basically at the charm production threshold, and then just using the perturbative machinery to start from this and evolve upward, and then basically constrain the normalization for the model, where the proxy is basically the size of the fitted charm moment, which is just the first moment of C plus C bar at that initial scale. And what you find is that in general, the variations in chi-squared, or the improvement in chi-squared, is extremely shallow. It's maybe something like 20 units of chi-squared, which is actually really quite small. There's a small signal at maybe about 0.5%, but in general, that's really not quite large. Is not quite large enough relative to the sort of tolerance or the precision that we have in fits of this type. You could look for this signatures at at the LHC as well. It would be an interesting way of doing that. And one possible avenue would be something like Z plus charm. For instance, LHCb has taken some intriguing data, for instance, in the form of actually ratios, the Z plus charm relative to Z plus inclusive jet. And there are 3 rapidity bins that in principle could have some sensitivity. So what's being shown here is actually on the left, a rapidity distribution in the produced Z for this ratio observable in particular. And what's most relevant is the largest rapidity bin, which is shown here on the far right. The various colorful points are basically the result in doing the theoretical calculation either at next deleting order in a fixed order calculation, or including some sort of parton showering effects as provided inside Pythia 8. And there's a very large spread in the theory prediction, basically independent of what you do for the fitted charm. That's shown on the left. On the right is the same calculation, in this case, just assuming the next deleting order fixed order calculation, now varying the input PDF. And what you would pay attention to, for instance, is these 2 red points, where this first one basically corresponds to no fitted charm, and the one immediately to its right assumes a particular fitted charm scenario. And the effect of doing that is really quite small relative to the other sort of theory of calculation effects that I just described. So this is a promising way. It could give us intriguing evidence going forward, but the idea is that we need to implement ideally some of the next and next deleting order calculations that have recently come out. And the larger point is that if you do fits of this type, again, what ends up being really essential is the PDF uncertainty in particular. So if you are getting very small delta chi-squared variations, in general, that is just too small relative to the PDF uncertainty in general, because if you just vary the PDFs, delta chi-squared can be much, much larger than that, as I showed a little bit earlier. Yes.
Can you ask a question on the 5 core clock states?
Maybe can we save it to the end, please? And yeah, so I'll don't forget. So yeah, just ask again. There are a couple more things that I want to just quickly mention since the time is rapidly dwindling. I did want to just say, since again, this is this EIC centric sort of meeting, that really, I think the best thing, the LHCb and sort of LHC measurements in general could be very promising and interesting. The ideal way of proceeding in this front, I think, is to actually just measure the charm structure function. And that in principle would be at our disposal at the electron ion collider, where again, you have this sort of tagging technology that you could imagine doing. And you could just measure basically the charm contribution to the F2 structure function. And that in principle is far more sensitive to what exactly is going on in the tails of the charm PDF. The lattice might also be able to tell us a little bit as well. So that would be another way of getting a handle. I have just a few more minutes. So are there any questions aside from, yeah.
A question on that intrinsic charm contribution.
Yeah. Okay.
Like, could you please comment if you know, like, when did they start to observe that contribution? Like, did they include some additional data set, like charm, jazz, whatever?
Oh,
When did they start to observe it? Are you referring to the LHCb in particular?
Yeah, that recent paper in Nature, I guess, right?
Oh, I'm sorry. Yeah, okay. Maybe we can save that to the end too. I'll just very quickly say, I mean, so that's just a different perturbative global QCD analysis, not unlike the CTEQ analysis that makes some different assumptions. And yeah, we can maybe discuss the subtleties and a little bit later. So I'm rapidly out of time. As I said, there have been a good number of questions, so I think I appreciate that. I think, a few more things that I just want to mention before concluding, while I still have your attention, is it's something that I want to stress is the fact that having the higher order QCD accuracy is again really important. And I wanted to show this just as a demonstration. This is the calculation again for an EIC-like observable. In this case, this is assuming EIC-like kinematics, charge current, deeply inelastic scattering at the level again of now just an inclusive cross-section plotted against X at a specific energy and a specific Q squared. And what you can see basically is the effect of doing this calculation at varying orders in just the perturbative QCD, starting at leading order, going all the way up to an approximate N3LO. And this also crucially takes care of sort of the heavy quark mass effects in the calculation that I described a little bit before. And that's a very subtle and complicated calculation. But the point is as I go to higher and higher orders, the variations stabilize in such a way such that I can control the scale uncertainties that I described in the lecture a little bit yesterday, and they become relatively small compared to the total PDF uncertainty. So again, you really want to have at your disposal these types of higher order corrections to ensure that the PDF extraction is actually robust and isn't dependent on a scale choice, and to control those types of uncertainties. The EIC can do many other things. So I want to just very quickly mention that, it's not just all about PDFs. The EIC can also, in principle, give us a better control over, for instance, our knowledge of alpha strong itself. That comes from just basically fitting inclusive data and just improving our knowledge of the strong coupling itself. Something similar is true for electroweak couplings too. We can go into a little bit more detail. I think the last thing that I'll just quickly mention before ending and taking any other questions is I wanted to connect to what Sally described a little bit earlier this morning. And what Sally talked about is this desire in particle physics to go beyond sort of model dependence in various analyses. In the case of what we heard about this morning, it was, of course, just searching for BSM physics, of course, in some sort of global analysis that doesn't depend on whatever your favorite model might happen to be. Your favorite model might happen to be some sort of supersymmetric scenario or something, or some 2 Higgs doublet model or whatever. You could take that model and then take your particular set of data and sort of compare, and then make your exclusion plot and sort of rinse and repeat. Ideally, what one wants to do is something that's more systematic and more model independent. And that's what this sort of SMEFT or EFT-based language actually does. It's very similar for the PDF fits. Once upon a time, people did something actually really quite similar there as well. You would have your favorite model for what the structure of the proton is, and then you would fit it to some select data. This state of the art now is to say, no, I'm going to flexibly parameterize things actually, and then fit all of the flexible parameterization to the world's data. The EIC actually rests in that landscape in a very interesting way. And that's in the sense that it can, of course, perform electroweak measurements that are sensitive to sine squared theta W, as I was just saying. And you might take that information and then try to perform some sort of global fit in some way that might be based on a specific attempt at parameterizing the BSM physics on the logic that I just talked about. This is this oblique S&T parameters that Sally described actually yesterday. But the better thing is indeed to do what Sally told us about at length, and to use an EFT, for instance, SMEFT, where you might, again, work at a particular sort of dimension, operator basis of a fixed dimension like dimension 6, as she explained, and then try to take maybe things like the EIC data that I just described and then fit all of that and get constraints to the Wilson coefficients of the various EFT operators. That's all great, but could anything go wrong with this? I'm taking hadronic data, right? I'm using that data to then fit things like PDFs. I'm using those PDFs and my knowledge of QCD, et cetera, to then make a theoretical prediction for some experiment. And then I look for deviations and signatures of BSM physics. What could possibly go wrong with that? Does anybody have a guess? Yes.
I mean, the BSM physics could be hidden in my PDF.
So this is, when I was a student, this was what I always worried about is how do I know? How do I know that when I fit these PDF parameters that there isn't, obviously there's not some crazy BSM resonance that I'm fitting away, but yet, as Sally told us, there could be a resonance at very high energies and you're seeing this tiny tail of that and you could end up shifting that somehow into the PDF parameters. So going beyond this, what you'd ultimately want to do is a still more universal global fit. And this is the theme that I wanted to really end the talk on. I mentioned the fact that, okay, we do proton fits. There might be some weird interplay with nuclear corrections and nuclear effects, and you can do nuclear PDF determinations too. You can do BSM fits with EFT. The direction of this field, I would argue, is toward more and more grand simultaneous fits to avoid the biases that could come into play and really spoil our understanding of things. We've taken some very tentative steps in this direction. This was a recent paper that we put out. Our colleagues in NNPDF have also done something similar. And the idea is that I take some very small number of EFT operators and corresponding coefficients and fit those alongside the PDFs. And in general, at the present time, there's very little indication of like a significant correlation, which is good news, right? So this is actually the fitted gluon. If I turn off or turn on these SMEFT Wilson coefficients and thereby introduce BSM physics into the global fit. But in general, what might happen is if I go toward the future and increasing experimental precision, sort of the size of the underestimation in the PDF uncertainty that might result if I basically don't simultaneously fit the BSM physics, that can become worse and worse going forward. And this weight basically corresponds to more and more data. So it's something that we expect we will have to keep track of. So with that, I think I'll just go ahead and conclude because I'm a little bit over time. The last thing that I was going to say is that we now have these interests in sort of machine learning techniques because this is such a large computational problem, inverse problem to try to do these types of grand universal fits that I was just describing. So with that, I think I'll just go ahead and conclude. I'll say I think in many senses we're at a really interesting and exciting moment. The EIC has a lot to do with that excitement because I think it somehow comes into its own in this really weird landscape of intriguing things going on at very high energies, new developments in computation and theory and so on. But what I want you to conclude, at least from today, if you learn nothing else, is that the EIC is not interesting just to itself. It actually will have an impact that really will be felt throughout particle physics and all of these different observables and theory calculations that I tried to just sort of show you some examples of. So the PDFs also more generally are a clearinghouse, if you'd like, in that space. And the last thing, I showed you a bunch of sort of vignettes, if you'd like, or here's a particular calculation, here's another. These are all pretty much all open issues. So each of these really could be a project unto itself. It could be an opportunity for thinking more in a collaborative sense. So I would invite you to keep thinking, ask me if you have questions. As we like to say here, don't be a stranger. Feel free to reach out if you have any questions or comments or anything at all. So thank you all.
Okay, so we'll pick up again at 3 o'clock, so enjoy.
Okay, great.
Can we ask questions or does that mean you go away?
I'll stay. So I mean, yeah, feel free. Anyone who wants to go and grab coffee, feel free. If you want to stay and talk more, then that's fine too. Maybe we can keep it to 15 minutes and I'll make sure. So, but anyone who wants to leave, feel free. Yes.
So I think I understand now why you're calling why that intrinsic that gluon splitting to CC bar is perturbative and intrinsic charm, when the gluons are coming off of two different fork lines. to
Yes.
Form a CC bar
Yes,
is perturbative because these two forks are in a bound state.
right,
There's something, so
right, right.
I'm gonna argue that both of those states are 5-quark Fock states in the proton.
Okay.
And that you're gonna get an interference to, when you add these things for intrinsic, for
Yeah.
CC bar content in the proton, you have to add the amplitudes for these things.
Okay,
So you're gonna get an interference term that's perturbative and non-perturbative multiplied together.
Hmm.
And that's gonna affect the charm PDFs.
but the question is how would you actually calculate that interference, like on the basis of a factorization theorem? Where you actually
Well,
separate, because I mean,
But Brodsky et al. Like 2022, or even more recently, but they're using.
but they always just use some model with fixed parameters.
They're using, I don't know if you would call it some model, James Barry does this too, but they're using.
Maybe now it's.
Model, yeah, it's a model.
But I agree, but I would argue that if you are only doing,
Sorry to interrupt, nothing wrong with that, by the way, I just want to be clear, models are great, I've done the same thing. A lot of these papers that I reference are mine
Of course.
building some model, that's okay, that's okay. It's just, the problem is like,
Why not?
that's one approach. Another approach is to say, all right, I'm actually gonna fit this from data without any of these like model assumptions present. So how to stick the two together, I don't know how to do it, and I don't think anyone does.
okay, so but my contention is that there's actually a model independent statement, which
How-
you are only doing
Yeah.
perturbative charm content. You are missing a significant, or it doesn't matter, forget significant, you're missing a part of it
Having a-
because there's an
instead of having
interference
like
term between the
100%
perturbative. and
launch or
non-perturbative.
now.
Yeah, I don't know, the other thing is, I don't know
Very
diagrammatically, how exactly.
Right.
No, but you feel free to, but yeah, I don't know how you would say this diagram is perturbative, this diagram is non-perturbative, because you need a scheme where you can actually organize those diagrams in a convergent series that's perturbatively converging. So that you can
A lot of
actually
the
say
stuff,
this
like
is
a lot of the,
perturbative,
if
this
you
is
could get a beat,
non-perturbative.
right? So I'm sorry, the reason why I'm sort of stuttering is like in my head, I'm like, how do
You
these
know, for the
very
1980s.
like, how are you gonna
Yeah,
get the
many
beats?
times,
Whatever.
right?
Whatever,
I
let's
know.
assume I have a beam, right? A beam
Yeah.
comes in and it scatters off
Uh,
something.
but
And so
maybe
you could
not
do
just-
exactly the same thing with
So-
electron beams right now, right?
Huh?
So,
Yes.
and
It's
now, like, for example, at JLab, the
Huh?
thing I'm doing is for
Okay.
vision
What is
management,
that?
science method,
This is intrinsic
with
charm.
electric
These are your
molar
fork lines,
states.
the ones coming off.
You could
CC
do
bar,
pretty
CC
much
bar.
the same thing.
One
Yeah.
intrinsic
Yeah, why
charm,
I asked
Five
about
quark Fock
because
state.
when I was in Atlas, I was searching
extrinsic charm,
Uh-huh.
the charge sheets, was searching in this tau channel, yet the
Proton.
charge
CC bar,
is going to tau nu.
five quark.
And
Right.
the biggest background is from W because W is
So,
big.
And the reason that this is non-perturbative is
Of course, you
because
have TT
these
bar.
are being created
Bar,
from
uh,
quark
yes.
lines that are bound together.
Yes, I understand. So I mean, this argument is from like 1984,
Also asked, sorry,
and I'm aware of this. I mean, I don't,
measure also an epi.
you still in the end
Yeah.
write down some sort of model.
Why
for
not?
this thing
You
on
have
the left.
polarimetry.
And then the thing on the
But
right
when the
is just, as you say, is just totally extrinsic, right? And so I'm now generating the CC bar. I mean, that's,
I mean, the
Yeah.
organism is
Yeah,
so low, right?
This is the good question, but this is why I asked about tau.
The infusion there.
Because then the
But- so the first-
much more
the
likely,
first,
I guess.
the first.
Yes, right. So your square root of S would be significantly
Yeah.
higher, yes. So
Yeah.
if you get, if you get your tau
This is,
to
this is
ACG,
extra. This is for
whatever,
DI.
yeah, that'd probably be a better bet.
Of not non-perturbative,
But I-
but
you know,
perturbatively generated.
I know.
With the-
I don't
I
think
know.
the tau decays, unfortunately.
This,
But,
so
you know,
so if you start,
there's
you
a,
start off,
in the BSM work.
I don't have this.
We are looking at
Start off.
charge flavor.
Because I have no, if I'm at the charm threshold,
So,
there's no non-perturbative
and
charm.
the,
If I assume
really,
in a model,
I mean,
if I assume in a global.
it was an idea
I
that
don't yet have this, I have to.
had
go above the
at
charm
UMass
threshold. It's this.
a while back.
So instead, if I produce
It's just a.
If I produce
Yeah,
charm,
I know
then
that's
it's
right.
three physics,
And
where I
the idea is to
charm, get the proton, then I start
at
off actually with a diagram that's like this. That's
measuring
actually
how
next to
no
me.
E. So if you get one of these events, you know, if you get enough events. And
But no, but so
basically you're
in this
looking
prescription,
at transition
this-
of electrons.